So if you recall, in the last lecture we had introduced gallium nitride transistors, and we are going to talk about gallium nitride RF transistors in this week. So we have 5 more lectures remaining, including today's lecture 30, okay, and we will take off from where we left in the last lecture in terms of iron and carbon doping to compensate the buffer in order to make the buffer layers more resistive so that you can block high voltages, okay. But we will go into the more finer nitty-gritty details of a gallium nitride RF transistor in the next few lectures, and towards the end of this week we will discuss about practical data sheets from commercially available AlGaN GaN RF HEMTs, how to interpret them and where the roadmap looks like, how the roadmap looks like. Okay, over to the whiteboard here. So if you recall, we are talking about an AlGaN GaN HEMT. That is because almost all commercial RF gallium nitride transistors are AlGaN GaN, and the substrate is by default silicon carbide, although silicon substrates are also now emerging in the market, but it is dominantly silicon carbide for reasons that we discussed in the last lecture. And by default there is always a thin ALN here, which I will not be mentioning again and again, but the understanding is that there is an ALN here again for reasons that we discussed in earlier classes, and the 2D electron gas stays here, right. And as I told you, typically when you grow on silicon carbide you have a thin layer of aluminum nitride, okay, a thin layer of aluminum nitride is grown. This is called a nucleation layer. This is called nucleation layer. It helps us to grow high quality gallium nitride on top of silicon carbide. If you grow directly there are other problems, okay, there could be background leakage might increase, the crystal quality will not be good, etc., etc. So we use a thin layer of silicon aluminum nitride and we grow gallium nitride. Typically there is a gallium nitride which is iron doped, and then after some time you stop the iron doping and then you do not dope this, this is undoped, no iron doping is there, and we call this the channel layer. This depending on the growth condition and the vendor, this could be say 200 nanometer, it could be even 500 nanometer, okay, this undoped region, and the dope region could be between 0.5 to 1 micron say typically. So the totals, and this is around 20 to 25 nanometer, okay. So the total stack thickness could be around 1.5 micron for instance, or maybe 2 micron, okay, depending on the vendor and what kind of wafers you are growing. And typically on top of AlGaN there is you can end the growth just here, but people usually put a small cap here, a very thin cap layer. The AlGaN layer, because it contains aluminum, the top layer could have more native oxides, and the things like current collapse that we will discuss could be more, so you typically put a thin layer. The thin layer could be either a gallium nitride cap around 2 to 3 nanometer, okay, or it could be even silicon nitride. This silicon nitride is called in situ silicon nitride because this silicon nitride is grown inside the reactor, such an MOCVD or MBE, without breaking the vacuum. When you are growing the stack, at the end of the growth you also grow silicon nitride before taking the sample out from the vacuum system. So we call it in situ silicon nitride. This is typically around 3 nanometer for instance, and it is found that this silicon nitride because of some, and this is also still an area of ongoing investigation, but silicon nitride, when you put a silicon nitride cap, people find that the 2D electron gas density that was there in the absence of silicon nitride, it increases slightly with the when you put an in situ silicon nitride, possibly because of increased stress in the layer could be one reason, okay, or modified Fermi level pinning could be another reason. But 2D density slightly increases, so in that case it is better, but again this needs optimization in terms of the growth of silicon nitride. You cannot just arbitrarily put any silicon nitride layer there, okay. So this is so much for the stack. This is the typical stack of an RF gallium nitride HEMT, and this is also what is mostly available commercially from vendor if you buy an epitaxial stack of AlGaN GaN HEMT. Of course people have different other stacks, academically people have investigated a wide variety, sorry, this is not the eraser, this is the eraser. So people have investigated, for instance, people have done this barrier as indium aluminum nitride, people may have tried aluminum nitride, okay. Nowadays people are trying even scandium aluminum nitride, which is a very strong polarized material, it's a ferroelectric material. So there are different materials that are being tried, but commercially and practically speaking AlGaN GaN HEMT still is the most common material and technology out there for AlGaN GaN for gallium nitride RF devices, okay, and this is all in gallium polar, okay, gallium polar orientation that we talked about. So, now if we come to more practical aspects of this transistor, this was just a stack, but if you are looking at a actual transistor, this is the 2DEG, okay. This is AlGaN GaN HEMT. You need a, of course, we have discussed field effect transistor in great details when we had discussed about gas HEMT, MOSFET, indium phosphide based p-HEMT. We have discussed generic discussion on field effect transistors, microwave field effect transistors, not just any field effect transistor. We discussed about many key concepts of field plates, gate recess, ohmic contact, etc., but we will discuss here in the context of gallium nitride HEMTs, okay, in the context of gallium nitride HEMT. So, of course, you have a gate here and you have a source and you have a drain. Typically what people do is that this source and drain, you need to make ohmic contact, that you already know, and because gallium nitride is a wider bandgap material, forming an ohmic contact is not very easy because it is the higher bandgap material. So, typically for source and drain contact, in RF technologies, people use a stack of something like titanium, aluminum, nickel and gold. This is a stack people used from bottom to top, okay, titanium, aluminum, nickel, gold, and then they alloy and then they annihilate at high temperature. It is called rapid thermal anneal. You can annihilate at high temperature, and though what thicknesses you use and what annealing temperature and conditions you use are again optimized based on the clean room and the process recipe. This could be typically say 20 nanometer, 120 nanometer, 30 nanometer, 50 nanometer commonly used. This ratio should typically be 1:6, okay. People have found that empirically, experimentally of course when I say empirically, and the annealing condition could be anywhere between say 800 degrees Celsius to maybe even 870 degrees Celsius or maybe even sometimes lower, and it has to be done in a nitrogen ambient, and it could be done for a half a minute to a minute for instance. Again, these conditions are ballpark numbers depending on the clean room, the wafer type, the processing recipes. This could drift and this could be changed here and there, okay. But what happens is that when you do this annealing, titanium alloy, you form an alloy, and the titanium essentially spikes down, forming titanium nitride below the contact, okay. The theory of ohmic contact formation is still investigated, by the way. It has been investigated for the last 20-25 years, but it's still, people still do TEM analysis and try to understand the role of different metals. But titanium nitride, it forms there, okay, and titanium nitride, what happens is that it's gathering nitrogen from the crystal. The gallium nitride crystal had nitrogen, and some of those nitrogen are basically taken by titanium to form titanium nitride. What happens is that in the crystal you create nitrogen vacancies, correct. You create nitrogen vacancies because titanium has taken away or sucked up the nitrogen to form titanium nitride, and nitrogen vacancies actually make the layer n-type doped, okay. It makes the layer n-type doped, so that is good for forming ohmic contact, okay, when your layer is n-type dope. So, titanium nitride creates nitrogen vacancies and helps create an n-type layer, and that n-type layer, n-type dope GaN layer below helps in formation of ohmic contact. And the aluminum, of course, aluminum also forms an alloy, and it is found that this titanium aluminum alloy further helps in reducing the contact resistance, and titanium aluminum alloy also spikes down, by the way. But you do not want to just end it with titanium aluminum because it can oxidize in the atmosphere. So, you have to cap it with a metal which is not so prone to oxidation. So, the top layer is gold. You put gold on the top, so that gold is very inert, it does not react so much with oxygen. So, it will help protect the metals below from oxidizing, or getting degraded. But the gold layer, and there is a titanium here and there is aluminum here, but gold and aluminum, if they alloy and form, they form this aluminum gold alloy. It is called purple plague, okay, and that is a very bad alloy because this alloy has a very high resistance which you do not want. So, you want a barrier here, that prevents aluminum and gold from actually mixing up, and that barrier typically is nickel, but people sometimes also use molybdenum, okay. So, that barrier prevents your aluminum and gold from kind of mixing up. But that being said, people have done transmission electron microscopy and they have found that gold exclusion zones can be also found below the contact, okay. Gold exclusion zones can be also found below the contact, still ongoing in study, but gold helps in reducing the contact resistance, is something that people have realized experimentally, okay. So, this is the ohmic stack, and when we are at the ohmic stack, what is the typical contact resistance that people talk about? Now, if you look from the top, this looks like a source and this looks like a drain, okay, and the gate finger could be this, which is closer to the source and away from the drain, of course, because this is the region that blocks the voltage, and this distance has to be as small as possible because you can have the source injection velocity. Okay, the source injection velocity can be high. You know, if you are very close to the source, you can inject the carriers better, but this is the region that blocks the voltage. Okay, and then the gate pad comes here where you are going to probe the device. Okay, and of course this entire device has to be isolated. You see this dotted line. This dotted line basically means that everything else here is etched away. The 2D electron gas is etched away, which means if I look at the side view of this, it basically looks like if this is your AlGaN, and of course aluminum nitride is there, I did not tell you that. If this is your 2D electron gas, then I physically etch the layer, and this is your GaN, okay, and this is your suppose silicon carbide. I etch it down couple of 100 nanometer until I get the doped iron doped GaN probably, and then this is physically removed. So, the next device will come here again, the source, the gate, the drain. So, this is device to device isolation. Okay. This is physical etching using a plasma. You can use a plasma such as example a BCl3 chlorine plasma. It's called dry etch. Okay, a plasma etch is called dry etch. You can use a dry etch in a plasma tool to remove this layer so that it becomes physically isolated, but in many fabs people do not do that. They use something called nitrogen implant. They implant nitrogen. So, this is not etched away, but if you implant nitrogen here, then this 2D electron gas gets sucked away, or you can say the 2D electron gas gets killed. So, if you have another device here for instance, sorry, okay, if you have another device here where the 2D electron gas is here, this 2D electron gas does not exist. This 2D electron gas is killed by the nitrogen implant. So, that is how people do in industry in many cases, because then it makes it a planar process. This is a non-planar process. You see there is a step here, then a step again comes up, right. This is a non-planar process. This is also done in industry, in 3-5 industry typically, but this planar process, you know, where you have done implant is done typically in CMOS fabs. So, if you are going to use a CMOS process, a CMOS fab line or foundry line, people might want to use this kind of a planar process as opposed to a physical etching process, but that being that's separate besides the point. But this is your isolated pad. So, their 2D electron gas exists only within this red square, and this is your pad. So, this is the gate pad. So, you probe there, and this is the source and drain. So, the source and drain current flows laterally, correct. The source and drain current flows laterally, we have talked about that. So, the current is always expressed in amp per millimeter, you know that, and the contact resistance is expressed in ohm millimeter. So, a typical contact resistance, a good contact resistance to start with for RF gallium nitride HEMT is about 0.5 ohm millimeter. Okay, this is called contact resistance, and I told you the sheet resistance of typical RF HEMT should be around 300 ohm per square. It could be 350, but should not be more than that typically, and people have gone up less than 300 also. You know, people can get 280 to 290 ohm per square in commercially available AlGaN GaN HEMT. I am talking about commercially available RF AlGaN GaN HEMT. Academically people have gone even below 150 ohm per square, but that is not something practically available in the market. So, typically, so 0.5 ohm per millimeter, it is based on the process, the clean room based fabrication process. So, this value is not something that your epitaxial wafer vendor will quote. If you buy an AlGaN GaN HEMT wafer from a vendor, this is the number that they will not be concerned about, and this is a number that it is not relevant to them. This is the number that is relevant to them because this is affected by the growth condition. The growth, when a material supplier provides you the wafer, the growth conditions under which they grow and the crystal quality that they grow will dictate the sheet resistance. So, this is a number that is very much very holy, very it's a sacred number, it is a biblical number for them. They will quote this number if you buy a 6-inch or an 8-inch wafer for instance, they will quote this number at different points of the wafer. It is 300, 305, 302, 310, 297. So, these numbers will be quoted in different parts of the wafer, but the contact resistance is purely process dependent. Depending on the clean room, depending on the process recipe, you are going to get different contact resistances. So, typically for an AlGaN GaN HEMT of 20 to 25 nanometer of AlGaN with 20 to 25% of aluminum composition with a 2D electron density of around 10 to the power 13 per centimeter square with a sheet resistance of 300 ohm per square, the typical contact resistance that you should get should not be more than 0.5 ohm millimeter. Okay, should not be more than that. This is good enough for RF HEMTs in, for instance, L band, which is 1 to 2 gigahertz, S band, which is 2 to 4 gigahertz, and even in C band to some extent 4 to 8 gigahertz. Okay, this contact resistance is not so bad, but you want to reduce the contact resistance further as you go higher and higher in frequency of operation or frequency at which you want the power, because with higher frequency operation your device is going to be shrinked because your device dimensions will shrink up. So your contact resistance may be the dominant factor that decides your delay. It could be the dominant parasitic factor, and you do not want the contact resistance to be the killer that defeats your or kills your device. So your contact resistance has to come down more and more as you go up in the frequency more and more. For instance, if you are talking about an X-band device in the 8 to 12 gigahertz range, you can still manage it at 0.5 ohm millimeter, but the device performance will not be optimal. You probably want a contact resistance lower than that, and typically around 0.3 ohm millimeter at least. Okay, you want it reduced. Similarly, if you go to even higher frequencies, say Q band, W band, etc., your contact resistance should be much lower. It should be around 0.1 ohm millimeter at least, or even less than that. Okay, you should go to lower and lower contact resistances for optimal performance. Okay, it all depends on what fraction of the total delay is contributed by the RC delay coming from contact resistance times capacitance, and it should be not the dominant factor that kills the device. Okay, when I say L band, S band, C band, etc., I mean you are extracting RF output power. You are extracting RF output power at these frequencies. This is not the cutoff frequency. Cutoff frequency is the frequency at which your gain is 1. We will come to that very soon. But these are the frequencies at which you are going to extract the RF power out of the device. Okay. All right. So we talked about the contact resistance in brief, and we talked about the device geometry in general. Okay, that's a 2-finger device. That's a single finger device, by the way. And so, okay, this is AlGaN again. This is GaN. As I said, so this is how you form the source and drain. This is how you form the source and drain. You isolate the device, of course. This is annealed, so the metal spikes down, and the 2D electron gas is here. Then you have a gate here. Okay, the gate here. Now in a 3-5 foundry, you can use gold, of course. So nickel gold is typically a good gate metal. People use 300 nanometer or 50 300 nanometer, etc., etc. Nickel gold, nickel also people use. Okay, again 30 nanometer, etc. So gate metal stack comes here, and people may sometimes do a soft gate anneal to reduce the leakage, but that's again process dependent. This is closer here, and as I told you, this distance, the gate drain spacing, LGD, the gate drain spacing, this LGD or the gate drain spacing determines your breakdown voltage. Of course, you know that, right, from your basic FET that we discussed anyways, but a higher LGD makes you get higher breakdown voltage, but it also increases the on resistance, or it increases the, in this case I will call it the drain excess resistance, RD. RD is the drain excess resistance, this. Okay. So the resistances that comes between the source and the gate, I call it the source excess resistance. The resistance between the gate and the drain is the drain excess resistance, and of course there is a contact resistance here, there is a contact resistance here. Okay, and then of course there is a leakage part that goes from here, which you want to minimize with iron doping anyways. Okay, so this higher, if you increase this LGD, okay, your the gate excess resistance also will be higher, and that will basically reduce your cutoff frequencies FT and Fmax. These are cutoff frequencies, will come to that. Okay, and so it's not good, you will have more delays and your power also will reduce, but you can get higher breakdown voltage, which also improves power because you want to apply a higher voltage to get higher power, and so it's always a trade off in the design. Okay, but this is your gate drain spacing. Now typically in an RF HEMT we do not use any gate dielectric. Okay, why? Because a gate dielectric is not needed, because this AlGaN Schottky barrier, the Schottky barrier that you form, the gate forms a Schottky contact, correct. The Schottky barrier is good enough for low leakage. Okay, good enough for low leakage, because in RF HEMT we do not go to 600 volt or 900 volt, unlike power switching. Typical AlGaN GaN HEMTs for power amplifiers, and I told you in the last lecture that AlGaN GaN HEMTs are typically used for power amplifiers, PA, although they are now increasingly also being investigated for low noise amplifier and switch. Commercially they are available, and even integrated TR modules are available, but still the dominant market is still the power amplifier. Gallium nitride, aluminum gallium nitride HEMTs can significantly outperform any other technology for power amplifier. Okay. So in power amplifier, you typically the bias voltage, you cannot arbitrarily in a given system, for instance in a cell phone, a cellular base station, I would say cellular infrastructure, cell phone base station, typical bias voltage is around 28 volt. Okay. So, you do not arbitrarily decide I will put it at 36 volt or 43 volt, not like that. 28 volt, close to 28 volt is where you typically bias the device. Okay. The next higher voltage that you people use is around 50 volt. There has to be a supply, if a DC, this is the DC voltage, the DC rail has to be has to supply a certain voltage, and so the availability of the DC rail matters. So, 50 volt is the next higher voltage that you use for AlGaN GaN HEMT. It could be for military, for instance in radar, it could also be for certain cellular application, but in typical this is for really high power, maybe jammers, maybe anti-drone jammer, etc. So, you use 50 volt supply, and very infrequently, very uncommonly people use also 100 volt. In real application space I am talking about, 100 volt supply rail is very less common, although it is not impossible, but there is probably only one vendor in the whole world who supplies AlGaN GaN RF HEMT which can be biased at 100 volt based on the data sheet. Okay, there is only one vendor as far as my understanding goes. 28 volt, dominantly 28 volt, 50 volt also there are vendors but fewer, and 100 volt is only one. Okay, but this is typically the way you go. So, it is not like you arbitrarily can bias the voltage at say 67 volt and get some power, you can do that, but this is not what we need, 28 volt, 50 volt and then 100 volt, these are the typical supplies. We do record power densities in AlGaN GaN HEMT, people have biased even at 150 volt. I mean that is mostly very difficult to get that in as a supply rail in a radar or in a satellite communication or in a cell phone. So, typically 28 volt is the most common, and then next is the 50 volt, you should keep that in mind. So, because you do not go to higher voltages like 600 volt, 900 volt, you do not need a gate dielectric. You do not need a gate dielectric because the gate leakage is already low at this voltage levels that we use. Okay. Secondly, the gate dielectric will add extra capacitance, the gate dielectric will not only add extra capacitance, but the gate dielectric also will introduce extra traps which will introduce extra hysteresis, those are the extra headaches that you do not want to take. Just a pristine gate is the best. Any oxide, any dielectric that you put below the gate leads to a probability of introduction of traps, hysteresis, unreliability, instability, etc., you do not want that. So, gate is directly put on AlGaN, or in cases where there is a top small GaN cap or a small silicon nitride cap, the gate is directly put on top of that, alright. And your leakage in RF world, in AlGaN GaN RF world is typically defined, the threshold for leakage is defined as 1 milliamp per mm, it should not exceed 1 milliamp per mm, but that is like the worst case scenario. Typically you would want much lower than that, tens of microamp per mm, maybe even couple of hundreds of microamp per mm, but no more. But 1 milliamp per mm is the threshold, you do not certainly want to exceed that for most of the RF application. Okay, that is the leakage parameter that is defined in that way. Okay. Now, source drain and gate has come, very good, but the significant important, and we know from AlGaN gas, pseudomorphic HEMT and HEMT literature, the discussion in the lectures, we know the concepts of field plate. We know that field plate helps improve, it helps improve the breakdown. Okay, it helps improve the breakdown, and so field plate is necessary. But before field plate, there is another very important, and that is the most crucial part, which is passivation. You need to passivate AlGaN GaN HEMTs, and this passivation is almost always universally using silicon nitride. Although academically people have researched other dielectric also, high K dielectric, silicon oxide, aluminum oxide, many other materials, but silicon nitride is the one that is most widely adopted, used, and also used in industry. Silicon nitride passivation is extremely critical for realizing and developing practically relevant AlGaN GaN HEMTs. Okay. And this is because it helps prevent or mitigate current collapse. Okay. Current collapse, and current collapse basically, as we had discussed earlier, is when you use it, when you make a transistor and you are basically plotting the output characteristics, this is ID, this is your VD, you are changing the drain voltage and you are measuring the drain current. Of course, at a given gate voltage you get a curve like that, correct. This is some gate voltage, and at a lower gate voltage you get something like that, at further lower voltage you get something like that. Eventually your channel is pinched off, okay, and higher gate voltage you get something like that, and beyond that you do not want to go because the gate will leak and turn on. Okay. So, different gate voltages, right, and of course that also translates to this IDVG that you all know IDVG. This is your depletion mode device because the channel is always on. So you have to apply negative voltage, say -4 volt, to turn the device off, and beyond -4 volt this is -3, this is -2, -1, 0, etc. the device will turn on like that. Okay, and you cannot go probably above 1 volt because the gate will leak, start leaking beyond that. Okay, so this is your DC condition, but and this is suppose 0, 1, 2, 3 up to 10 volt. But if you go to higher drain voltages, you need 28 volt on the drain. As I told you, typical supply voltages are 28 volt. Okay, if you go to 28 volt, what will happen is that this current will start drooping because of a combination of heating and trapping. The current will start decreasing, it is called a droop, and that happens because of heating if you are doing a normal DC measurement. Okay, or it could be also trap related, where the trap comes into picture with higher temperature and they capture more electrons and the droop happens. Okay. Now the way to avoid heating in at least in measurement, maybe not even practical application, but in measurement, is to do pulse. Pulsed, what does pulsed IV mean? You are going to pulse the drain and the current voltage of the current and the drain. So there are different, in pulsing you can use different question points, Q points. Q point stands for the biasing points. Okay, where are you going to bias the device? Q stands for quiescent. Okay, where are you going to bias the device? So the Q point could be gate and drain voltage is say 0, 0, and this is called a pulse condition under cold fat. The name cold fat means that there is no heating, you eliminate heating, so it is a cold fat. It does not mean that the temperature of the device is very cold, it means that you are eliminated or you are mitigating effect of the heating as much as practicable by having this condition. So what does 0, 0 mean? It means if you have suppose an IV which looks like that, okay, IDVD, it means that after every, so you measure it after in different grid points, right, you measure it after say every 0.1 volt like that. This is how the tool, your Agilent or Tektronix or Kitely or whatever system you have, it measures after each point of say 0.1 volt or 0.05 volt, etc. right. So and this is the value that you get at different points. So at each point, for instance, I take this value, I measure this current and voltage at each point. After measuring there, I come back to 0, 0 value. This is the point where the drain is 0. This is also the point where the gate is 0. I'll assume, I'll put the gate also as 0 at this point. Then I'll go back and I'll measure this point. Then I'll again come back. Then I'll go back and measure this point. Then I'll come back. Then I'll go and measure this point and I'll come back. Okay. So this happens in pulse, right. I keep the device on, this is on, right, and this is off. I keep the device on, this is on, this is off, correct. So I keep the device on for say 1 microsecond and I keep the device off for say 100 microsecond. So the duty cycle could be 1:100 or something like that. Okay. So this helps you dissipate the heat. At 1 microsecond the device was on, but the device is off for 100 microsecond. So you give more time, 100 times more time for the device to dissipate the heat. So it could be even sub microsecond by the way, and this is where you kind of mitigate the effect of cooling as much as possible. In that case you do not get the droop that you saw like that. Okay, you do not get the droop like that, you get a very good curve, a straight curve like that. You get curve ekdam that looks like this, okay, no droop. Okay, so that is called cold fat condition. Now what is current collapse? We probably have talked about it. Current collapse is basically when you put some stress on the gate or the drain, the current will collapse. It means the current with respect to this cold fat condition will reduce. What it means is that if my question point is say Vg and Vd is equal to say -6 volt and 0 volt, whereas the threshold voltage is say -4 volt, which means in an ID versus Vg my device looks like that. So this is suppose -4 volt, okay, so it is off state here -5, -6. I go to this point, correct, I go to this point -6 and that is on the gate, and I go to drain equal to 0 after each point. So I have something like, suppose I have this point, correct, this is the data that I need, and this is at different points I have different values I am getting. So after each point here, suppose I measure this point, I go back to Vd equal to 0, this point, this is Vd equal to 0. At the same time I put Vg equal to -6. So there is a below pinch off, this region is below pinch off, right, below pinch off. I allow the gate to be stressed, okay, I allow the gate to be stressed, I go to off, then I come back again on, okay. So this on off again happens. The on of course is smaller and then off is longer, and that is how you do it. It is called gate lag, it is called gate lag condition, alright. So actually there are two things here, one is the gate lag kind of talking about, and other is the drain lag, okay. Very important in the context of current collapse and passivation in GaN HEMT, okay. Current collapse and passivation is very important for the device people to address these issues in order to get reasonable or acceptable output power from an RF HEMT. So essentially I am already talking about gate lag here, where you go from a certain, so for instance this is your ID and this is your VD, your family of curves looks something like that. So at every point, for instance this point, you measure, and then for a pulse say 1 microsecond, and then for another set time, for instance 10 or 100 microsecond, you come back to 0 volt on the drain and say -6 volt on the gate, assuming the pinch off is at -4 volts. So you go below the pinch off, okay, right. So I already said that. So this is your ID and this is your Vg. So suppose -4 volt is your threshold or pinch off, so your current goes like that. So you come to -6 volt here, so it is below pinch off, but on the drain you apply actually 0 volt only. So that if you look at the gate and this is the drain and this is the 2d electron gas, so then this is at 0 volt and this is at -6 volt, okay, for this duration. So then you do not extend the depletion on this side because it is at 0 volt on the drain. So it is not so much, you are not exerting a field between the gate and the drain except for this -6 volt, okay. So this is your gate lag, and your current, for instance if I choose the red color, the current might collapse to some extent. So this is that, and this is the second curve, this is the third curve. So what is happening is that at -6 volt you are essentially looking below the gate. So whatever traps or other impurities or imperfections are there in this region, if they capture the electron and if they are not able to release the electron on time, then you will have this lag. Essentially what happens is that your gate will go to this pulse, it will go to off state, and again it will come back, again off, again come back. Can these traps capture and release, or emit and release, emit and capture the electrons as fast as these pulses? If they can, then you will see no collapse of the current, and if they cannot, then you will see the current is collapsing or the current has a lower value, and that is called the DC to RF dispersion or current collapse, and that is a bad thing, because then what happens is that in real application you are not going to get any power, or you are going to get less power, okay. And very slightly it also extends the field towards this side because there is a 6 volt bias between the gate and the drain. So slight portion towards the right of the gate, towards the drain also you kind of deplete, and so this part also has to respond as fast as to the as fast as the train of pulses is repeating, and then in that comes the concept of virtual gate. I will come about it in more detail when I talk about drain lag. So there is a concept of virtual gate which will be useful in basically understanding why this lag happens, okay. So for instance if I come to now drain lag, so that was gate lag, right. Now if I come to the drain lag, it is the same measurement except that the drain is also pulsed now. So for instance I am going to pulse the gate and the drain, okay, at say -6 volt and say 30 volt. What it means is that I am going to apply a large bias on the drain to stress the device. So if this is your IDVD, for instance, this is your 10 volt, 20 volt, 30 volt on the drain, and this is your current, of course, right, and this is suppose gate voltage of 0, gate voltage of -1, gate voltage of -2, gate voltage of -3, and then gate voltage of -4 is the pinch off, okay. So -5, -6 also will be here because it is below pinch off. So now what happens is that I go to this point, for instance at say for 1 microsecond I measure, then for the next 100 microsecond for instance I will come back to this point, which is at 30 volt of drain, and the gate is at -6 volt. I will come to that condition. So -6 volt on the gate means that it is below pinch off, and 30 volt on the drain means that this is your gate and this is your drain, right, and this is a 2dG. Now this is -6, so this is pinched off here, and the drain is at 30 volt. So there is a lot of field between the gate and the drain, so some part of this is also depleted, okay, some part of it is depleted, and so because it is blocking this 30 volt, no, so it is a high stress condition. You are not only depleting this, the field lines also go deep into the buffer. So you are reaching deeper layers in the buffer, you are also reaching on the laterally, you are also depleting the 2 dg below the between the gate and the drain. So two things are happening, one is the surface is coming into play more prominently now, I will come to that, and secondly your field lines are also penetrating deeper. So you are reaching deeper layers of the HEMT stack. So you are kind of reaching out to the traps, maybe there is a iron doped or carbon doped layers there. So those traps will start mattering now, in a sense ki they will be capturing releasing electrons slowly, and that will lead to a significant collapse. So now what will happen is that your drain leg current will be very less, something like that. This is for 0, this is for -1, this is for -2. So that decrease, the percentage decrease in the current that has happened from the cold fed condition to the drain leg condition is the current collapse under drain leg, and you are essentially pulsing both the gate and the drain, okay. And the collapse is more significant under this case than in the gate pulse only, because only in the gate pulse or in the gate leg, as I have already told you, you are only looking below the gate and slightly to the right perhaps, but here you are looking below the gate, you are also looking significantly towards the gate drain extension region, you are looking also deeper into the buffer. So it is a more complicated process now in the gate drain pulse, double pulse, which is also called drain leg, okay. So the concept of virtual gate is important in both these cases, but more prominently it is important in the drain leg. So what happens is that if you have a gate for instance and then you have a drain here, so you see this 2D electron gas, they are they physically they come from the surface donor states or surface traps which have donated the electrons, and that is why the electrons are here. Now when your gate is say pin stop -6 volt, okay, and your drain is at certain volts, say 10 volt or 30 volt, you have depleted this part below the gate, but you also have depleted to some extent here on the lateral side, because that is what is blocking the 30 volt here, right. That is the depletion that is happening. So when it is depleted, because of the high field between the gate and the drain, one dominant theory is that your gate will inject electron, okay, the gate will inject electron which will basically neutralize these surface states. So these surface states are neutral now, they are no longer positively charged, and that is why this depletion region extends, essentially this depletion region extends here, okay, that is blocking the voltage. Now when you go back from -6 to 0 volt, when you turn the channel on, so this part is no longer depleted, it comes back, 2 dg comes back here. However this part, this part here, it may not be able to respond as fast, it may not be able to respond as fast. Why cannot respond as fast? That is because this traps on the surface to give the electrons back again and become positively charged donors, it will take certain time. That is point number 1, okay. The surface states will take certain finite amount of time to actually give the electrons back and come back again as positively donor charged, and so the coming back of the 2D electron gas here will also take some time. Secondly, there is also buffer, the field lines are penetrated inside the buffer, there is carbon dope, iron dope, etc. So this buffer traps, dislocations, all these defects, etc. may also capture electrons, and they may not be able to release as fast. Because of both of these phenomena, this part will have a lag, okay, it will take some time to come back, and that is why as opposed to the cold fed condition, your drain leg condition, the current will collapse like that. This is a collapse that is happening, okay. So that is a bad thing, and because of this collapse your current will be low, and because in a real microwave signal, when you are putting an input signal and you are going to amplify the signal, you are kind of mimicking this large signal pulse only. So if your current has dropped by say 30%, then in a real RF power amplifier your current will be 30% lower, and that is a significant setback, because you are not able to get as much current as that you want. So the way to solve it is of course twofold. One is the buffer has to be good, which means your material quality has to be really good, low defects for instance, low dislocations, because those are all potential centers of capture and release of electron. You need to have also the iron doping and the carbon doping that you do should be as far away from the 2D electron gas channel as possible, so that the field lines do not reach there, okay. If they are super close to the 2D electron gas, then they will be easily penetrated by the field lines from the gate drain region, and then they will start capturing releasing electron. That is a bad thing. So those things you have to take care for the buffer quality. Your structural and the crystal quality will matter significantly. And the second thing is your passivation. So passivation, people generally do a silicon nitride passivation, and that can be deposited by tools like plasma enhanced chemical vapor deposition, or ICP, inductively coupled plasma chemical vapor deposition, or low pressure chemical vapor deposition. In some cases people also do MOCVD, okay. These are different techniques to deposit silicon nitride. Say about, people have different recipes, they can deposit say around 100 nanometer of silicon nitride. Where do they deposit it, and what happens here? So you have a gate here, correct, and then you have a drain here, right, and then you have a 2D electron gas here. So you have the positively charged donor states here. This is actually the virtual gate, by the way, this part. So you put a silicon nitride passivation, like you blanket deposit silicon nitride passivation like that. So, this could be 100 nanometer thick silicon nitride for instance. You do not neutralize the traps, you basically protect the traps, okay. You protect the traps here, okay. These traps you protect so that the electrons cannot go and basically neutralize them, okay. So, that way you enable this 2DG to respond faster below this part. However, these traps getting neutralized and not neutralized is also the reason why this 2DG can get depleted below the gate drain access region, and that actually blocks the voltage, the breakdown voltage. So, if you passivate, what happens is that your surface traps cannot be neutralized, or they cannot be neutralized by this gate injecting carriers, and so your device will respond faster. So, essentially if your cold fed condition look like that, then your drain lag also will be very low, because you're basically not allowing them to get neutralized as much. So, you will have less collapse, but the compromise that you have to make, or the trade off that you have to make, is that the breakdown will be sacrificed, because this depletion region will also not extend as much, and this depletion region will be compromised, because this depletion is sustained by this surface traps getting neutralized and again not neutralized. So, if you are preventing that surface traps from getting neutralized and not neutralize that cycle, then you are essentially preventing this depletion region also from forming as much, and so your breakdown is to some extent compromised. So, an exceptionally good passivation scheme will lead to a lower breakdown, okay, and so that is a compromise you have to make. So, you want some amount of collapse, maybe 10% collapse, but you want the breakdown to be not so compromised, so that you can still bias your device at 28 volt or 50 volt as the case may be. So, this is the concept of the passivation and the virtual gate. You want to protect the surface traits, you also want the buffer quality to be very good, so that both of these conditions will lead to a reduced current collapse in general. And the difference between gate lag and drain lag is that in gate lag only below the gate you are primarily looking slightly towards the gate drain side, but in drain lag you are looking not only below the gate but also deep into the buffer and also towards the surface between the gate and the drain, the lateral depletion, okay. So, drain lag actually is a more realistic assessment, and people therefore rely on drain lag more to understand the collapse. In gate lag, if your crystal quality is very good, you may not even see a collapse, it will be very minimal, okay. And if your crystal quality is bad, then you will also see some gate lag dispersion. Also, people sometimes see that with a passivation also improves gate lag, by the way. So, it is a complicated interplay, and a good passivation scheme is not very easy, because it will depend on whether the silicon nitride that you are putting, is it tensile stressed or compressive stress, for instance, what is the refractive index of the silicon nitride. All these things will matter in terms of coming up with a very good silicon nitride passivation recipe to protect your devices, okay. And once you have the silicon nitride recipe, you can again put field plate on top of that, for instance. You can have a gate first process, you can have a gate second process, etc., but those are the later stage. But what is more important now to understand is that your current can collapse under pulsing, large signal pulsing, and we need to fix this current collapse in order to be able to get meaningful power out of a gallium nitride RF device, okay. And silicon nitride passivation is the key to enabling that, okay. So, with that we will conclude this lecture here, and I would like to thank for your time for going through this discussion here. So, in the next lecture we will continue from where we are leaving, and we will probably talk about the process of gate first and gate second, the field plate and things like that, okay. So, thank you for your time, I will see you in the next lecture.